Good afternoon. My name is Minos, and I will be presenting about OpenCI for trusted firmware. Trusted firmware comes with 3 configurations, two of which already contain some sort of tests. The default configuration is intended for production builds, so it does no special testing. The core test build configuration is intended to validate the functionality of the TFM core module, and it is very closely bound to the platform hardware, and special consideration should be taken when introducing a new platform to the system when porting the core test. Regression test builds are mostly aimed at testing the TFM services. There should be platform agnostic, but as the services will extend and there will be more variants with optional functionality, it will be quite possible that we will be having specific services that will fail in platforms because they don't have the optional hardware. So this is an example of the output of a board running a build using regression tests. When the system boots, it will produce the output of the test using the serial interface. It is colorized for readability reasons, and tests are grouped based on the service that you are testing, which is quite obvious here. It's quite verbose. And they're also grouped based on the side that you're running them. If you're running secure tests, if you're running the test on the secure side, on the non-secure side. In the end of each side, there is a summary appended, which is quite useful as a way to demonstrate, to have an overview of what has passed and what not. So in order to develop an OpenCI system for TFM, we need to have a system that is, first of all, robust, but also needs to be quite versatile. It needs to scale, and it needs to be extended for specific platform requirements. So there are some unique challenges that we need to address, such as how do you merge different type of binaries, and how do you verify that the binary block that you have created is correct. Also, how can you validate that the hardware which is controlling the housekeeping controller, which is responsible for controlling the hardware during the test, is running a proper firmware and is doing what you expect it to do. Also, you have to manage a lot of different variants of different build configuration, different platform configuration, and this is taking an effect in time. This will cost you time. And in addition to the system being quite versatile and try to address as much needs as possible, it needs to be easy to use, and it should not distract the developer. It should not disrupt the flow of the developer. Last but not least, it's quite important that the system is easily extended and can hook itself to existing OpenCI solutions like Jenkins, Travis, and other stuff. So controlling the hardware is one important aspect of real hardware testing. The software, the CI software, needs to be able to programmatically power cycle a board, needs to be able to flash the board, needs to be able to reset the board, and needs to be able to communicate with the board. In addition to that, the software needs to be able to control the flow. There are certain steps that it might need to block and wait, some steps it might need to skip, and so on. It also would be quite good to have some sort of feedback from the actual hardware to be aware of at which stage you are currently at. This is quite helpful with timeout. And there is a possibility that in the future, more smart ways and more extended functionality will be added to those housekeeping hardware controller firmware. We should be able to detect whether that functionality is present and use it if possible as an optimization measure. So this is a a small example of the boot sequence on an ARM IoT board. This is intended to show the discrete steps that are being taken, that the boot sequence takes, and that would be useful for the CI system to either intercept or be aware of the state of it. So originally you have the board powering up, and then in ARM boards we have a doubling microcontroller. It's a housekeeping microcontroller that provides a virtual drive interface for the flashing using drag and drop, and also it exposes one of the serial ports from the application board as a virtual serial port. The doubling, once it has powered on, its secondary role is to validate that all the other components of the board are in proper state, check some clocks, and then power on the main application MCU, which contains a subsystem that we're running our application on. At this moment, for example, it would be quite beneficial for our system to be able to block the flow and start testing right before the application MCU reset, or stop testing if something is not correct in the hardware itself. When the application MCU powers on, you get the normal boot. By default, you're booting in secure vault, at which point TFM will launch. It will set the security attributes for this specific example, and then it will fall back to the non-secure OS, at which point testing should be complete. So testing has a lot of platform-specific constraints which we need to take into account. So aside from different hardware variants and existing or non-existing optional hardware contained in a platform, some tests might fail, some service-related tests might fail. But also, platform execution time is board dependent. If you have a platform booting from RAM and you have a platform booting from QSPI with execute in place, timeouts might be triggered. You need to take that into account. Also, the flow of programming a board, resetting it, or even getting output out of the board might be different in different platforms. Our system needs to be able to determine those variations and account for it. The code size is another concern, because different compilers produce different code size binaries. In platforms with limited memory space, in a embedded world, we don't have the luxury of infinite space and infinite RAM. We need to be able to test for that and also be able to capture faults in that side. Last but not least, there is not a common agreement on how to implement the debugging UART interface. Some of the boards use a discrete UART interfaces, some of the boards use jumper UART interfaces, some others multiplexing UART interfaces. So you might be coming across a situation that you are running the proper firmware and not getting any output because the wrong UART interface is producing the output. With TFM, we currently can have 12 different build configurations. We can build TFM using GCC or ARM CLang. We can build TFM using the built-in MCU bootloader, or we can build it without it. And for each of those combinations, we can build either regression, default, or core test configuration. 12 different configurations, they do have an impact in time. And this is critical for the development workflow. So, with time, we need to test everything, but can we afford to test anything? We cannot. Using the 12 different examples on a board, as I mentioned before, running with execute in place from QSPI, regression test will take more than 10 minutes. Just testing a single platform will take over an hour. Testing every single platform will take several hours. We cannot afford to do that for every single patch. So, the question is, how are we prioritizing builds? Which builds should a developer be testing before he pushes a patch upstream? And assuming on the back end that we use parallel builds for different platforms to optimize the hardware testing, this will significantly increase the test farm hardware requirements and will add synchronization issues. And in the end, the question is, how much testing is considered adequate, and how much can we be smart about it. Synchronicity is an interesting issue. Synchronicity is about validating that the code that you're running and that you are testing is the one that you expect to be testing. So assume a scenario that you have a normal CI-friendly board that will automatically boot when you power it on and will automatically run the binary. The system powers on the board in order to copy the binary, and at this time, the previous binary produces an output text. This output text, if captured and not properly flashed during the testing stage, it will pollute, it will contaminate your serial output and will fail or will cause you to pass a test that you're not meant to pass. On the similar side, if you have a board that will automatically boot and it will be faster than the system expects it to be, assume that you have a delay between the deploy and the monitor stage, the board will produce some text that you're going to miss, and again, you're going to fail a test. It is quite important to be able to synchronize what it is running and what the system expects. And it would be ideal if we could just add a synchronization command that will tell the hardware to run the test now when I tell you to. But there are several implications that we cannot just do so. So let's discuss about the proposal of the OpenCI for TFM. I'm just gonna lighten the mood a bit and move on. So what we're suggesting is to use a high-level scripting language in combination with a container technology system. The idea is that we will be testing we will be testing locally and we will be testing remotely. And in addition to that, we will be doing nightly tests. The condition that those happen will be explained in the following slides. The most important is the process should be backend independent. The process should be spread in discrete stages that perform a single task and that hand over a specific report to the next step to work with it. So the first step should be building the configurations requested. It will produce a report which is the list of binaries. The next step will take this report and will run it in hardware or simulated software and get the output. And the final step will parse this output using regex matching and determine whether the test had the expected output or not. Hardware simulation control should be abstracted, and there should be a common interface, and the system should not really care how you're running the test. All it should care is, this is the binary I want you to run, and this is the output that it produced. Obviously, the system should also provide standardized modular hooks in order to hook it with Travis, Jenkins, Lava for building the system, for testing the system, and so on. And it is also important that we not only test for faults, we validate the logic if it does something that does not seem right. And we also capture things like code size increase or performance affecting changes. And obviously, in the last step, we should be producing a report using an open format, restructured, markdown. This is to be determined, but that's something that needs to be easily exported and converted to different formats or added to the build artifacts. Testing the binaries. Testing the binaries, we have two different ways of validating the binaries that we have just built. Simulation, QEMU is a typical example that can be used on any other simulation software. And the idea would be that we will be testing the functional behavior of the program. We don't expect to have a variant of the simulation software and support for every single platform. This is more like a first look into the logic of the system. And then we will need to be testing on discrete hardware, especially because of the timing constraints that this might create. So when it comes to the hybrid development flow that I just suggested, there should be a logical order of how to run the tests. On the user side, you should be able to use the scripts provided to pull down a Docker or any other container technology image containing the environment that allows you to build and run the tests on your side. And you should be required to test the GCC compiler, but no limitation of you performing more than the bare minimum tests. If you want to test GCC compiler and ARM-C-Lang, you can do so. If you want to test in live hardware as well as simulation, you can do so. The first step would be obviously to use linting tools to check for the code style. Then try to compile, verify that that works. The next step would be to run the tests, at least in simulated platform if the developer does not have a board himself, or with a board. Then it will generate a report containing all the information about every test that has been locally performed, and will attach it to the pull request as he pushes it back to the system. That way the backend will already know how much this patch has been tested from the user. And this is mostly for scalability reasons. On the backend side, Travis, Jenkins, or whichever tool we decide to use, the system will trigger using the pull request, will read the report coming from the user, and will try to test every single platform every single variant of the 12 variants for this specific platform. So if I want to push a patch for Masca, the backend will automatically test all 12 variants for Masca. If the backend is very busy and there are hundreds of pull requests going on at the same time, it might choose to deprioritize or skip some of the tests I have already done on my machine. Passing this test will give a provisional +1 score to the system, but this will not be enough for the changes to be merged, because the next step, the system will start aggregating all the patches that have come in the last 24 hours and create a collateral concentrated patch. And we'll try to test them all during the nightly phase for every single platform configuration. And this is important because you might push a patch for a board A, and that works perfectly on board A, but it might totally corrupt the behavior of another board. So it is quite important to be able to use a time window at night to test for every single possible configuration. So when it comes to the nightly testing, if you aggregate a lot of different patches together and they all pass, you assume that this is the intended behavior, and you also assume that when those become substream, they will behave as expected for every single platform. So by doing so, you have managed to optimize your time requirements for testing every single patch individually. The interesting situation is what will happen if you get the aggregated nightly build to fail. In this case, the system will need to decide if this was if this contained a lot of patches. I might use a binary search algorithm trying to isolate the patches that break the build, and then score everything else independently, or I'm just going to do sequential patch testing and try every single patch on its own on every single platform and score it with +2. So this is the generic overview. Questions?
Hello. I'm a little puzzled. You talk about doing hardware testing of secure boot code, but if the secure boot code is controllable externally, then it isn't that secure. So I'm kind of puzzled by the chicken and egg problem of how do you test real hardware, secure code on real hardware externally and control it. Because you talked earlier about having to be able to control the hardware flow of the secure boot, but you shouldn't be able to, if you do that, then there's something wrong with your secure boot architecture.
Yeah, I'm assuming you're referring to this specific, to this one. Are you referring to this one?
And maybe before, one before, I think.
You mean,
Yeah,
or this one?
no, not before. Yeah, that.
Okay.
Yeah, someplace you talked about testing, having hardware control to do the testing, but I don't see how you can have hardware control if you're doing secure boot. If you have external control, then secure boot isn't secure.
Yes, basically when I'm referring to hardware control, I'm mostly referring to the doubling. So I'm basically referring to a housekeeping interface that will allow you to control the hardware before TFM and before normal boot has been performed. This is a development board, and in most cases, even in a production board, you can use a stage 2 bootloader, which is what we provide as a way to verify the root of trust on the secure side. So if something goes wrong in the bootloader side, the TFM test will fail if you implement something wrong. I'm assuming that in production, a lot of those things will not be feasible. For example, the way that you're flashing the firmwares during the product development life cycle will lock down certain aspects. So this reference design is mostly about testing it on development boards, that you are permitted to do more things that you would be in a production board.
Yeah, in our case, we don't have a DAP link, and in our development boards, if you put them in secure mode, you still have the same thing as a production. There's no distinction. You have no control once you put it into secure boot. You can't undo that, and and we don't have a DAP link or anything like that. So I'm just, I guess maybe then in that case you do a QEMU simulation or something. I'm not quite sure what you do for the testing of this.
Yes, but we will always need to test hardware. So the question is, if we don't have a DAP link, we would need to have something that mimics certain functionalities of the DAP link. The most important thing of the DAP link is functionalities like drag and drop flashing and stuff like that, or exposing the serial controller. This could be done by an external hardware. If the board, for example, does not have a built-in SoC to do that, you can do it using external hardware. At this specific chain, the question is, we need to control the flow until this moment, at the moment that you are booting the application SoC, which is the security-aware one. I'm not sure if...
Well, yeah, in our case, we have a fuse that once you set the fuse, it says whether you normal boot or secure boot. And once you've set it to be secure boot, it can't be undone. And there's no way to get in, there's no way to get external control of that process. You just have to make sure you write the code properly.
Okay, but when you set it to secure boot, and you expect to run TFM, you will be running a production build. I mean, can you unset the fuse, or is it a one-way fuse?
So if I could add here,
Yes.
correct me if
Okay.
I'm not representing it correctly. You need a way of flashing the device, and if you have a production device which doesn't have a lot of housekeeping hardware, then you could as well use the firmware update process for that particular use case, for that particular device, and burn or flash the new binary image. So all of this infrastructure is just for letting the new binary being put into the device. And if you have a device which doesn't have the extra peripheral, you could as well use the firmware update process to put new firmware, do a reset, and then use the harness provided by the CI infrastructure to run the runtime tests.
Okay, but then if you do that, we also have NV counters that prevent rollback of software. So once you've built this secure thing, this testing thing, you can't go back to the production one. You have to kind of go forward. You know what I mean? And again, like I said, you can't turn off the secure boot, can't undo it. Once you set it, it's permanent.
So some of these production devices that I have worked in the past will have some sort of production switch as well. So you have the device in the development phase, and by flipping that OTP, you'll say that fine, from this point onwards, it's all security protected. You can't do rollback. You can't do. Basically, you have limited number of bits in OTP, so you can only fuse so many times. And if you put your device in the CI, after I don't know 256 operations, you need a new board. So I guess that's the scenario you're talking about. Usually, you would implement something in the software which will disallow burning the OTP until you have switched the device from the development phase to the production phase. So you can still do the firmware update. You can, without really burning out the OTPs, you can still do download the new firmware. But at that time, you know the device is in the development phase. Once you flip the device in the production state, there's only limited things you can do there.
So I just wanted to know why it will take 10 minutes to finish one configuration test. So usually MC code is relatively simple without a rich OS. Okay.
Yes, this is just an example that a board can be quite slow. Access to a specific SRAM or a specific QSPI can be quite slow. On a normal flash board, it should not take long. On a normal MPS2, it will not take that long. So most of the tests that take a lot of time are those that are validating the secure storage currently, which is quite a complicated procedure because it's a set of unit tests that are doing writes and verifications. And to that, the speed of your flash interface actually matters. So I'm just assuming that not everybody will use the same type of memory, and it's quite possible that will trigger some hard-coded timeouts if you try to take that into account.
But it can be that some tests need to do things that last long. It depends upon what the test scenario is.
But if it takes that long, like what prevents you from having multiple boards running the same, like different configuration?
Yes, this is one of the, I suggested that before. This, you can afford to do that on the test farm, but the problem is that this will be quite hard to scale in the future. So assuming that you have 50 boards that will be running TFM or 100 boards that will be running TFM, and for a single patch you need to test every platform, it will be quite hard to scale. The idea is...
Why? What prevents you from scaling?
That normally you can either run a lot of tests in the same board, or you run 10 boards in parallel for different configurations. So assume you have 50 boards, and you have 12 different configurations just for TFM, including anything else that comes from extending the project. And you have like 100 pull requests, 100 patches pushed in the same day.
Yeah, but what prevents you from, say, having 500 boards, not 50?
Yes, naturally that's another option. We are considering that, but just pointing out that time is an issue, and we need to determine on how to do it properly that satisfies everybody's need. The idea will be that there will be a centralized hardware dispatcher, but then if a partner wants to add their own hardware testing facility, they can just connect to that. So you can be able to, if for example you want to be running things faster and you want to contribute like 500 boards in your own test farm, you can do so. But the rules are not set yet. This has to come back from feedback.
Okay.
I think the difference about pragmatic choices and what is actually possible in theory is where. Okay.
The only problem is space, right?
Yeah.
This is the problem behind it. There's no problem with software, there's no problem with hardware scaling, it's just space.
Okay.
There's another way to handle this thing in a slightly different way. For every single patch, you don't have to run 50,000 tests. Well, today tests are only limited. We still, and that itself takes 10 minutes or probably more than 10 minutes in some cases. Is going to get even worse. So we have to rationalize what tests are required for what kind of changes. And then after that, we need to set up some sort of nightly builds where you run everything on the master branch. And for a specific patch, we need to find out what is more relevant and try not to run everything there. And hopefully that will solve some of the problems there.
Okay. Okay, thank you.